Betelgeuse has always been a star that grabs attention, not just because of its size, but because of the mysteries surrounding it. For centuries, astronomers have watched its fiery glow shift and flicker, wondering when it might make its next big move. And well, it's doing something unexpected again. This time, it's brighter than anyone expected. Astronomers using the James Webb Telescope have noticed a sudden increase in its brightness, and it's caught everyone off guard. Now, scientists are trying to figure out what's going on. Could it be a sign of something bigger? We don't know yet, but one thing's clear: whatever is happening with Betelgeuse cannot be ignored, so keep watching to find out. Something is seriously wrong with Betelgeuse. Betelgeuse is a red supergiant, which basically means that it's a star that has reached the final stages of its stellar evolution. Located roughly 642.5 light-years away from Earth, it is one of the largest and brightest stars in our galaxy, about 700 times the diameter of the Sun and more than 10,000 times as bright. Stars like Betelgeuse are known for their instability as they near the end of their life, often showing irregular dimming and brightening cycles. However, this latest intense surge in brightness is unlike anything astronomers have seen before, which makes it a significant event in astrophysics. Betelgeuse isn't only a red supergiant, it's also a pulsating semi-regular variable star. That means there's some periodicity in its brightness changes, though the amplitudes can vary. It has an approximately 400-day cycle where its brightness changes. It also has a shorter 125-day cycle, another 230-day cycle, and a whopping 2,200-day cycle, all determined by pulsations. All those cycles can make the star difficult to understand clearly. A couple of years ago, Betelgeuse dimmed, and people wondered what that meant. The episode is called The Great Dimming, but more on that later. Now that Betelgeuse is brightening again, scientists are paying close attention. They want to understand what stage of its evolution the star is in and what this recent activity might indicate about its future. And in order to do this, they are using the James Webb Space Telescope. Does this increase in brightness spell danger for humans? The James Webb Space Telescope, designed to study the universe with exceptional precision, played a crucial role in detecting this change. Using its infrared capabilities, JWST was able to see through the layers of dust and gas around Betelgeuse, providing scientists with a clearer view of the star's surface and surroundings. What the telescope revealed was extraordinary. Betelgeuse's brightness had increased by 250% in just a few weeks, a rapid and unexpected shift that indicated something unusual was happening within the star. The implications of this sudden increase in brightness could be game-changing. For one, Betelgeuse has long been a candidate for a supernova event, a massive explosion that occurs when a supergiant star exhausts its nuclear fuel. While Betelgeuse is expected to go supernova sometime in the next 100,000 years, this new burst of energy raises the question of whether that moment might be approaching sooner than anticipated. Research suggests Betelgeuse could go supernova much sooner than expected, possibly within a few decades after its core exhausts its carbon fuel. Scientists believe Betelgeuse is currently in the late stage of core carbon burning, and its carbon supply could run out in less than 300 years. After that, the star could explode within just a few decades. However, it's difficult to pinpoint exactly where Betelgeuse is in its life cycle. The surface of the star doesn't show much change in these late stages, so while it's clear Betelgeuse is nearing the end of its life, whether it will explode in a few decades or a few hundred years remains uncertain. What would happen if Betelgeuse exploded? If Betelgeuse does go supernova, it would be an unforgettable sight. Massive stars like Betelgeuse explode as Type II supernovae, collapsing violently after burning through all their fuel. While the explosion would be dramatic, Betelgeuse is about 642.5 light-years away, well outside the 160 light-year danger zone that could pose a threat to Earth. Still, there could be unexpected effects from the supernova. For example, animals that rely on the moon for navigation might get confused by the sudden burst of light. Even astronomers would face challenges. Observing the night sky would be tricky with such a bright object shining for months. But despite these minor disruptions, a Betelgeuse supernova would be an extraordinary event. The last nearby star to go supernova was in 1604, and most other supernovae occur too far away to observe without powerful telescopes. Betelgeuse would be the closest supernova ever witnessed by humans. When Betelgeuse explodes, it would shine as brightly as the half-moon for more than 3 months. It would be visible in the daytime sky for about a year and continue to be seen with the naked eye at night for several years as it slowly fades. Scientists predict we'd have some advance warning of the explosion. Instruments on Earth would detect neutrinos or gravitational waves produced by the event up to a day before the explosion. Imagine the world watching Betelgeuse together, waiting for the light show of a lifetime. Anyone alive on Earth when Betelgeuse does finally explode will see an amazingly beautiful sight in the night sky, a very, very, very bright star. Meanwhile, amateur astronomers and casual stargazers will enjoy the explosion too. But the many who enjoy seeing Betelgeuse as Orion's bright red star will dearly miss it when it's gone. This isn't the first time Betelgeuse has scared us. The great dimming, all the buzz about Betelgeuse going supernova started in 2019, when the star suddenly dropped to about 40% of its usual brightness before gradually returning to normal by early 2020. The astronomers who first noticed Betelgeuse's dimming, Richard Wassertarnik, Edward Guinan from Villanova University, and amateur astronomer Thomas Calderwood, believe that a combination of a regular 5.9-year light cycle minimum and an unusually deep 425-day period could explain the phenomenon. Other possible causes proposed in late 2019 included an eruption of gas or dust or changes in the star's surface brightness. By August 2020, after long-term studies primarily using ultraviolet observations from the Hubble Space Telescope, researchers suggested that the dimming was most likely caused by a massive amount of superheated material ejected into space. This material cooled and formed a dust cloud that blocked light from roughly 1/4 of Betelgeuse's surface. Hubble observed dense, heated material moving through the star's atmosphere in September, October, and November, before other telescopes picked up on the more significant dimming in December 2019 and the first months of 2020. By January 2020, Betelgeuse had dimmed by a factor of about 2.5, dropping from a magnitude of 0.5 to 1.5. By February, the Astronomer's Telegram reported a new record minimum brightness of plus 1.614, noting that the star was now the least luminous and coolest it had been in 25 years of observation. The star had also experienced a decrease in radius. This bizarre dimming caused some speculation about an imminent supernova, as Betelgeuse had fallen out of the top 10 brightest stars and now appeared dimmer than its nearby neighbor, Aldebaran. Media reports fueled speculation that the star might explode soon, but astronomers pointed out that while Betelgeuse is expected to go supernova, this is likely to occur sometime within the next 100,000 years, not imminently. By the 17th of February 2020, Betelgeuse's brightness had stabilized for about 10 days, and by the 22nd of February, it appeared to have stopped dimming altogether. On the 24th of February 2020, no significant changes in the star's infrared readings over the past 50 years were detected, suggesting that a core collapse was unlikely. Instead, scientists believed that large-grain circumstellar dust could be the primary reason for the star's dimming. A later study, using sub-millimeter wavelength observations, ruled out significant contributions from dust absorption. Instead, researchers proposed that large star spots might be responsible for Betelgeuse's dimming. While similar events happen on our Sun all the time, Betelgeuse's ejection was about 400 billion times more massive, and the chunk the star spewed into space was probably several times the mass of our Moon. So, in reality, Betelgeuse didn't actually dim during the Great Dimming. It just looked that way because we were looking through a cloud of stellar debris. But all the worry around this mysterious star is well placed. Betelgeuse is very unpredictable. Stars like Betelgeuse are notoriously difficult to predict, as their size and complex internal dynamics create conditions that challenge even the most sophisticated models. Betelgeuse, in particular, has confounded astronomers for years with its erratic light patterns. Understanding why its brightness has suddenly surged by 250% could offer new clues about the life cycles of red supergiants and the processes that drive their fluctuations. One theory that has emerged in response to this event is that Betelgeuse may have experienced a massive convective cell, or hot bubble of gas, rising from its core to its surface. Such convective events are common in supergiant stars and can cause significant changes in brightness as material is ejected from the star's outer layers. If Betelgeuse did indeed experience such a convective event, it could explain the rapid increase in its luminosity, as the hot gas released into space would temporarily brighten the star. Another possibility is that Betelgeuse has shed a significant amount of mass in the form of a stellar eruption, creating a cloud of dust and gas that may be interacting with the star's light. In 2019, Betelgeuse experienced a mysterious dimming event, which some scientists believe was caused by a large mass of dust obscuring part of the star. This latest brightening could be a reversal of that process, with new material being ejected and illuminated by the star's intense light. Another intriguing hypothesis is that the star's magnetic field may be playing a role in these changes. Betelgeuse's magnetic activity is not fully understood, but recent studies suggest that it may have a complex and dynamic magnetic field that could influence its brightness. Changes in the magnetic field could alter the way energy is transported through the star, leading to rapid fluctuations in its luminosity. If this is the case, the current surge in brightness could be tied to a shift in Betelgeuse's magnetic activity, which might provide a new avenue of exploration for scientists studying stellar magnetism. As astronomers continue to monitor Betelgeuse, the sudden increase in brightness also raises questions about the role that stellar mass loss plays in the evolution of supergiant stars. Red supergiants like Betelgeuse lose mass at a prodigious rate, shedding large amounts of gas and dust into space. This process is thought to play a key role in the final stages of a star's life, as the loss of mass can affect the star's structure and stability. If Betelgeuse is indeed losing mass at an accelerated rate, this could signal that it is approaching a critical point in its life cycle, one that may lead to further instability and, eventually, a supernova. But there should be no need to panic because, according to scientists, this sort of phenomenon is common for massive stars. And the only reason why Betelgeuse makes the news every time is because it's so easy to see. Throughout history, scientists have closely observed Betelgeuse due to its brightness and proximity to Earth. Because of its brightness, even the earliest humans likely noticed Betelgeuse, and it features prominently in the mythology of various cultures. Though many today recognize it as part of the constellation Orion, named after the hunter in Greek mythology, the ancient Egyptians included Betelgeuse in their constellation Osiris, the god of the underworld. The ancient Greek astronomer Claudius Ptolemy even described Betelgeuse using the Greek word hypokyrous, meaning a color ranging from pale yellow to light reddish. This suggests that, in ancient times, Betelgeuse may not have appeared as red as it does today. Aboriginal groups in South Australia have oral traditions recounting Betelgeuse's variable brightness that stretch back over 1,000 years, which underscores the significance of the star in human history. In more modern times, Sir John Herschel observed Betelgeuse's brightness variations between 1836 and 1840. He noted that the star outshone Rigel, another bright star in Orion, during certain periods, particularly in October 1837 and November 1839. After a quiet decade, Herschel saw another cycle of variability peaking in 1852. Over the years, records show unusually bright phases, with some smaller variations, particularly between 1957 and 1967. Betelgeuse even shone brighter than Rigel, leading Johann Bayer, who catalogued stars in his Uranometria in 1603, to designate it as the alpha star of Orion, despite Rigel being generally brighter. In Arctic regions, where Betelgeuse's higher position in the sky gives it prominence, the Inuit referred to it as Aluria Juak, meaning large star. In 1920, scientists Albert A. Michelson and Francis G. Pease, with help from John August Anderson, used a 6-meter interferometer at Mount Wilson Observatory to measure Betelgeuse's angular diameter, finding it to be about 0.047 arcseconds. Although they derived an approximate diameter of 3.84 times 10 to the power of 8 kilometers, 2.58 astronomical units, uncertainties arose due to limb darkening and measurement errors. Two major developments in the 1950s and 1960s impacted how astronomers understood stars like Betelgeuse. First, the stratoscope projects, which sent balloon-borne telescopes into the upper atmosphere, provided high-resolution images of solar granules and sunspots, confirming the existence of convection in stellar atmospheres. Second, Martin Schwarzschild and Richard Hahn published Structure and Evolution of the Stars in 1958, offering theories about stellar convection in red supergiants and advancing the use of computer models in stellar studies. In the 1970s, significant strides in astronomical imaging technology began with Antoine Labourie's invention of speckle interferometry, which reduced the blurring caused by the Earth's atmosphere. This technique, along with advances in infrared telescopes at Mount Wilson, Mount Locke, and Mauna Kea, allowed astrophysicists to better study Betelgeuse's complex circumstellar shells, where they suspected massive gas bubbles created by convection. These technological breakthroughs culminated in the 1980s and 1990s when astronomers began using aperture masking interferometry on Betelgeuse. This method revealed detailed images of Betelgeuse's photosphere, including bright spots on the star's surface, which supported earlier theories about convection cells on red supergiants. In 1995, the Hubble Space Telescope captured the first ultraviolet image of Betelgeuse's disk, offering a higher resolution than ground-based interferometers. This image revealed a bright patch in the star's southwestern quadrant, indicating a region about 2,000 degrees hotter than the rest of the surface. Subsequent studies using the Goddard high-resolution spectrograph suggested that this hot spot corresponded to one of Betelgeuse's poles of rotation, giving astronomers clues about the star's orientation relative to Earth. Now, just because everyone can see Betelgeuse doesn't mean everyone understands it. So let's see why the star has seen a 250% increase in brightness. The real reason behind Betelgeuse's increase in brightness. To delve deeper into the implications of this event, it's important to explore not only the scientific and technical details but also the broader cosmic and philosophical consequences of this unexpected brightness. Betelgeuse, a red supergiant at the terminal stage of its life, has always been a fascinating object of study due to its peculiar and irregular behavior. Yet this most recent development, the unprecedented increase in brightness, has forced scientists to reconsider established models of stellar evolution, particularly for supergiants. The sudden surge raises fundamental questions about the forces at work inside Betelgeuse that could cause such a dramatic shift. As with many large celestial bodies, Betelgeuse is governed by complex interactions between gravity, fusion processes, and magnetic fields, each of which could be contributing to its recent outburst of luminosity. One area where this event may provide critical insights is in the study of stellar fusion. At the heart of every star, including Betelgeuse, nuclear fusion reactions generate energy that counterbalances the force of gravity pulling the star inward. In a supergiant like Betelgeuse, these reactions are more complex than in smaller stars like our Sun, because the core's extreme temperatures and pressures can lead to the fusion of heavier elements beyond hydrogen and helium. During the final stages of a red supergiant's life, these fusion processes become increasingly unstable, as the star struggles to fuse heavier and heavier elements until it can no longer sustain the energy required to counteract gravity. The 250% increase in Betelgeuse's brightness could indicate a dramatic shift in its fusion processes, possibly involving the fusion of heavier elements in the star's core. As it runs out of fuel, the core contracts and the outer layers may react violently to changes in the star's internal structure. This could result in large-scale ejections of material, which could momentarily cause the star to brighten significantly. In this context, the recent brightening could be a prelude to more violent convulsions within Betelgeuse, bringing it one step closer to its inevitable demise as a supernova. However, this increase in brightness is not merely a sign of impending doom. It also sheds light on the often overlooked phenomenon of stellar mass loss in supergiant stars. Betelgeuse, like many other stars in this phase, has been gradually losing mass over time through stellar winds and outbursts. These ejections of gas and dust form intricate clouds surrounding the star, which can obscure its light or cause it to shine more brightly depending on how the material interacts with light emitted from the star. This process is crucial to understanding the life cycle of supergiants, as mass loss directly impacts their structure, stability, and eventual supernova explosion. The James Webb Telescope could be the key to unlock Betelgeuse's mysteries. As the star continues to be monitored, particularly by JWST with its unparalleled ability to capture infrared wavelengths, scientists will gain more precise data on the processes occurring within and around Betelgeuse. The telescope's ability to peer through the clouds of gas and dust surrounding the star provides a clearer view of the mechanisms driving these sudden changes in brightness. With JWST, astronomers are not only able to track Betelgeuse's light variations but also study the composition and structure of the material it ejects, shedding light on the star's mass loss and internal dynamics. Typically, variability in stars follows relatively predictable patterns, governed by factors such as pulsations or binary interactions. Red supergiants like Betelgeuse, however, are more erratic due to their immense size and the dynamic conditions within their outer layers. This variability often defies simple categorization, as seen in Betelgeuse's case, where an unpredictable surge in brightness presents new challenges to existing models of stellar evolution. To understand Betelgeuse's sudden brightening, scientists must also consider the role of pulsations, another form of stellar variability common among supergiants. Pulsating stars undergo periodic expansions and contractions driven by imbalances between gravitational forces and the outward pressure generated by fusion in their cores. These pulsations can lead to observable changes in a star's brightness, temperature, and size. In the case of Betelgeuse, pulsations may be contributing to its recent luminosity surge. Some red supergiants experience long, secondary periods, where significant changes in brightness occur over extended timescales, possibly driven by large-scale pulsations that alter the star's structure. If Betelgeuse is entering such a period, the 250% increase in brightness could be just one phase in a longer, more complex cycle of variability. Further, the JWST's discovery brings to light the interaction between Betelgeuse and its surrounding interstellar environment. Betelgeuse has been shedding material for centuries, forming a vast shell of gas and dust around it. This circumstellar environment, composed of elements ejected during the star's life, plays a significant role in how Betelgeuse's light is perceived from Earth. Dust, in particular, can absorb and re-emit light, which can either dim the star or, as may be happening now, amplify its apparent brightness depending on how this material interacts with the star's radiation. Betelgeuse's brightening may result, in part, from changes in the distribution of this circumstellar dust, which could be reflecting more of the star's light toward Earth, or allowing more of it to pass through. The material ejected from Betelgeuse also serves as a laboratory for studying the life cycles of massive stars. As the star sheds its outer layers, it contributes to the surrounding interstellar medium, enriching the galaxy with heavy elements. This process, known as stellar nucleosynthesis, is responsible for producing many of the elements found in planets and life forms, including carbon, oxygen, and iron. Betelgeuse's current activity, including the release of material that may be causing the brightness surge, is thus part of a much larger cosmic story, the continuous recycling of matter in the universe. Stars like Betelgeuse act as cosmic forges, producing and distributing the elements that will one day form new stars, planets, and potentially life. This leads to another fascinating avenue of inquiry prompted by the brightness increase, how this material will affect the future evolution of Betelgeuse. As the star sheds mass, its internal balance of forces is altered. This mass loss can destabilize the star, potentially accelerating its progression toward a supernova explosion. The amount and rate of mass loss could provide critical clues about how close Betelgeuse is to the end of its life. Some astrophysicists believe that red supergiants like Betelgeuse undergo periodic outbursts that expel vast amounts of material in the years leading up to a supernova. If this is the case, the current surge in brightness may be a precursor to an even more dramatic event in the near future. Looking beyond Betelgeuse's immediate behavior, this event also has significant implications for our understanding of stellar evolution in general. One area that has been particularly challenging for scientists is understanding the exact triggers for supernova explosions in red supergiants. Betelgeuse, being relatively close to Earth, offers a unique opportunity to study this phenomenon up close. If its current increase in brightness is indeed related to its impending explosion, astronomers may have the chance to observe the lead-up to a supernova in unprecedented detail. This could provide critical data on how the internal structure of red supergiants changes in the final moments before a supernova, helping to refine theories about the mechanisms that drive these cataclysmic events. Betelgeuse's activity may also offer insights into the mysterious phenomenon of supernova imposters, events where stars brighten dramatically but do not end in a true supernova. These imposters can sometimes mimic the behavior of stars about to explode, but instead of a full-blown supernova, the star returns to a stable state after ejecting some of its outer layers. It is possible that Betelgeuse's recent brightening could be an imposter event, a temporary outburst of energy that mimics the early stages of a supernova without leading to the star's immediate destruction. If so, this would provide valuable data on a phenomenon that remains poorly understood. In addition to its role in stellar evolution, Betelgeuse's brightening also has implications for our understanding of the broader cosmic environment. Supernovae are critical drivers of galactic evolution, as they release vast amounts of energy and matter into space, triggering the formation of new stars and reshaping the structure of galaxies. If Betelgeuse is indeed nearing a supernova, the explosion could have far-reaching effects on its local galactic environment. The shockwave from the supernova would sweep through the surrounding gas and dust, compressing it and potentially igniting the formation of new stars. This process, known as triggered star formation, could lead to the birth of a new generation of stars in the Orion constellation, where Betelgeuse resides. Moreover, Betelgeuse's supernova could provide an opportunity to study cosmic rays, high-energy particles that travel through space at nearly the speed of light. Supernovae are one of the primary sources of cosmic rays, which are thought to originate from the acceleration of particles by the shock waves produced during the explosion. If Betelgeuse were to go supernova, scientists would have the chance to study the production of cosmic rays up close, potentially answering long-standing questions about their origin and behavior. The event also underscores the importance of multi-wavelength astronomy in studying stars like Betelgeuse. While the JWST's infrared capabilities have been instrumental in detecting the recent changes in Betelgeuse's brightness, other wavelengths of light, such as X-rays, ultraviolet, and radio waves, will also be crucial for understanding the full picture. Each wavelength reveals different aspects of a star's behavior, from the high-energy processes occurring in its core to the cooler, more diffuse material in its outer layers. Coordinating observations across multiple wavelengths will allow scientists to build a more complete understanding of what is happening inside and around Betelgeuse as it undergoes this dramatic transformation. The sudden increase in Betelgeuse's brightness has also sparked renewed interest in its role within the larger field of stellar astrophysics. Researchers estimate that Betelgeuse has been a red supergiant for around 40,000 years, having left its main sequence phase approximately 1 million years ago. During this time, the star has undergone short periods of significant mass loss. Estimating how much mass the star has lost overall remains challenging because Betelgeuse moves rapidly through space as a runaway star, making it difficult to compare current mass loss rates with the total lost mass over time. The surface of Betelgeuse shows signs of nitrogen enhancement and lower levels of carbon, along with a higher ratio of carbon-13 to carbon-12. These indicators suggest that Betelgeuse has undergone the first dredge-up, a process that occurs shortly after a star enters the red supergiant phase. This means that Betelgeuse has likely been a red supergiant for at least a few thousand years, with predictions that it has already spent about 40,000 years in this phase. Scientists estimate Betelgeuse's current mass at around 19.4 to 19.7 solar masses, based on evolutionary models that calculate how much mass it has lost. However, this estimate is considerably higher than other methods suggest, such as using pulsation properties or limb darkening models. Betelgeuse is expected to end its life in a dramatic supernova explosion, like all stars more massive than about 10 solar masses. Stars with masses up to 15 solar masses typically produce a Type 2P supernova from the red supergiant stage. However, more massive stars, especially those that rotate or lose mass quickly, may evolve into hotter stars before their cores collapse, leading to other types of supernovae. The timing of Betelgeuse's supernova remains uncertain, depending on how long it has already spent as a red supergiant. Estimates suggest it could explode within 100,000 years, though the exact timing depends on whether Betelgeuse is a rotating or non-rotating star. Its birthplace in the Orion OB1 association has seen several supernovae, which may have caused nearby stars like Columbi, Ae Aurigui, and 53 Orites to become runaway stars. One thing is for sure: when Betelgeuse finally explodes, it will release enormous amounts of energy. A typical Type 2P supernova emits about 2 times 10 to the 46th joules of neutrinos and produces an explosion with a kinetic energy of 2 times 10 to the 44th joules. As seen from Earth, Betelgeuse would shine with an apparent magnitude between -8 and -12, making it visible in daylight. Although its brightness might not exceed the full moon, the supernova would be a dazzling sight for months before it begins to dim. Let's just hope we see it in our lifetime. All right. So, what do you think about this discovery? Do you think it's a precursor for a supernova? Or is there another reason for this strange phenomenon? Let us know in the comments below. If you enjoyed this video, be sure to click the like button and subscribe for more exciting content. See you next time.